Hi, my name is Rodney Nash. I'm a protection and control engineer for Parasurf Technologies in Riviera Beach. I work on Florida Power and Light Systems in South and Central Florida and next era generation facilities all over the country. I've just spent almost 30 days in Dodge City, Kansas working on a huge wind farm generating power to a collector yard. My project is going to be capturing solar radiation by photovoltaic arrays. We'll boost the voltage as necessary. We're going to invert the voltage for home use. We will rectify and buck the voltage to go back to a battery bank. Control decisions will be made by a Schweitzer Engineering or SEL 487E. It's a standalone control relay that can do voltage and current, fault location. It's a one controller designed to do all. Hopefully we'll be able to reduce costs by selling back to the grid. My project will be done on solar arrays, where you have small photo cells that have to be put in series to gain enough voltage and in parallel to gain enough current for the average home use. My solar array, each photocell can produce a half a volt at optimal condition. These photocells are put into modules with a combined voltage of almost 5 volts, and all these modules put together is going to give me a photo array of 121 volts. That's good enough for this project to simulate what's actually going on. Voltages could be anything you want depending on the number of arrays. If we do not have optimal sunshine, we'll be using a boost converter to boost the voltage up. If we don't have optimal conditions for each photocell, it's going to drop the voltage enough that we need to boost it up so we can maintain or regulate a proper voltage to the home. Here's a slide of my boost converter. Voltages or whatever I choose them to be. It's basically a 3-to-1 ratio. If I drop down too low, I can go as high as 3 times higher. Again, we will regulate this to make sure that we have about 125 volts going into the home. You have a 3-phase inverter, which is going to come off the photo array or boost converter if necessary, which will take 3 sinusoidal signals at 120 degrees apart to give you a smooth, stable voltage and current. Again, for the local load or their home use or home's use. You can do multiple transformers. Each home should be single phase. Here's a slide of my 3-phase inverter. Using pulse-wide modulations, you just take the DC signal, turn it into square waves, and then you're going to have to smooth it out into sinusoidal waves using inductors and capacitors. The signal is going to be 60 cycles per second. 120 volts per phase. After the local load at your home has got enough power, anything excess will be put back into the battery banks. So we'll change this AC signal back into a DC signal through a rectifier and through a buck converter if necessary. Here is a diagram of my AC-DC rectifying circuit. Take it put it through diodes, chokes, smooth it out, making a nice smooth waveform to go into the batteries. Buck converter will take the voltage that may be a little bit too high and regulate it and keep it to the voltage necessary of about 128 volts to my battery bank. Again, here's the buck converter circuit. See, we have 140 volts coming in and maintaining very close to 128 volts output for storage into the batteries. Now, once the battery banks are full, the local load is satisfied. We'll take these battery banks and possibly get ready to invert it back to the power grid. This is the battery banks. When they reach less than 50% or whatever number that I choose, will recharge. Sell it back to the grid when everybody is full or at capacity. This will all be controlled by an SEL487E. Again, we spoke about that earlier. It is voltage control, current control. This controller is good for fault location, trip breakers, bus differentials. If we have any type of differential in the bus or the system, it'll trip on that also. Future research is windmills and parabolic collectors. DC windmills is basically used all the time. It doesn't matter what the wind speed is and how fast, how slow. You're just charging a battery, set of batteries. It really doesn't need too much of a control system. What's being used out there for the most part is AC synchronous windmills. You have blade pitch, which changes with the wind speed to make sure that the motor maintains 60 cycles per second. If the windmill, if the wind is too fast or too slow, the windmills will shut down by feathering the blades, and the blades will actually lock in a position once motion has stopped. Controller will unlock them when the wind is the proper speed. We have technology out there for parabolic mirrors or dishes instead of a PV array that can actually drive a mechanical hot-cold engine called a Stirling engine, which will drive a DC generator. Current technology does not allow a Stirling engine to drive fast enough for a synchronous machine. Some research needs to be done on that to see if we can actually make one fast enough and be able to maintain synchronous speed. Research also needs to be done on controller costs, battery bank storage. Batteries are extremely expensive, and controllers are very expensive. In my conclusion, the solar PV array captures only during sunlight. If it's partially cloudy or starting to get dark, the sun just coming up, we're going to have to boost the voltage. We have to make sure that the DC to AC voltage to the home is always the correct voltage. We use voltage rectifier to ensure that the voltage is the correct voltage to the batteries. Control decisions are based on load and battery usage to where the switches are actually set to where they're actually going to go. We have to make sure that when we switch back to the grid that we are synced with the actual backbone of the power company so we do not have a problem. We have to make sure that we actually engage at the exact moment of time. Hopefully we'll be able to recoup our energy, our cost back as the energy is sold back.